Have you ever looked at a massive bridge or a soaring airplane and just wondered, how does that not break? Well, it's not luck and it's not magic. It's an incredible field of engineering called load modeling. Today, we're going to pry open the engineer's toolbox and see exactly how they make all those invisible forces of stress and strain totally visible, predictable, and most importantly, safe.
All right, so here's our game plan. First, we're going to talk about the problem itself, these invisible forces all around us. Then, we'll dive into the toolbox and check out 3 layers of tools: the classic foundational toolkit, the powerful digital workbench, and the seriously futuristic intelligent assistant. And finally, we'll put it all together to see how these tools let us model our world in ways that are just wow.
Okay, so let's start with the invisible forces. This is the core challenge, right? Everything, and I mean everything, from the chair you're sitting in to the phone in your hand, is in a constant battle against pressure. An engineer's entire job is to make sure the things they build win that battle, every single time.
Which leads us to the big question, doesn't it? How do you design something to withstand all that punishment, day in and day out, for years or even decades? Well, the answer is kind of like being able to see into the future. It's about predicting with incredible accuracy how things are going to behave long before they're even built.
And that's exactly what load modeling is. It's this amazing blend of art and science that turns those invisible stresses into hard numbers. It's a whole suite of methods, math, computers, physical tests, that lets engineers figure out the absolute limits of their designs. It's all about making things safe and built to last.
So, time to pop open that toolbox. The first thing we find inside is the foundational toolkit. You can think of this as the bedrock of engineering. These are the classic, tried-and-true methods that have been the backbone of the profession for generations.
These are the trusty hand tools of the trade, you know? They're the proven formulas you find in textbooks, the fundamental laws of physics, and, really importantly, the actual hands-on tests that prove a design works in the real world. It's all about rock-solid calculations and real, tangible measurements. And this toolkit really breaks down into 2 main approaches. On one side, you've got the analytical methods. This is the pure math, the established industry standards like ISO 281 for figuring out how long a bearing should last. Then on the other side, you have the experimental methods, which is, and this is the fun part, literally breaking stuff in a lab just to see how much force it can actually handle.
And you can see just how varied this toolkit is. An engineer might use something called fracture mechanics to figure out the exact spot a tiny crack might form in an airplane wing. Or for something huge like a bridge, they might bring a full-scale steel girder into a lab and just bend it until it snaps, all to prove that their math holds up in the real world.
But, hand tools can only do so much. So now we move on to the next layer in the toolbox, the heavy-duty power tools. This is the digital workbench, and it's all about computer-based simulation.
The absolute star of the digital workbench is this game-changing technique called the finite element method, or FEM. What it does is brilliant. It lets a computer take any complex object, like say a car engine, and break it down into millions of tiny, simple pieces. Then it can simulate exactly how forces or heat or vibration flows through the whole thing. It's literally like having a lab inside your computer.
And engineers use these incredibly powerful software programs, you might have heard of some, like ANSYS or SolidWorks, to run these simulations on just about anything. We can model the massive forces acting on a skyscraper's walls, or we can zoom way, way in to see the stress building up inside a tiny metal part just millimeters across. The scale is just amazing.
This really shows you the massive leap forward this represents. The foundational methods are great for standard problems, for sure, but digital simulation lets us test wild, complex, real-world shapes and run thousands of virtual tests. We can tweak the design over and over again to make it lighter, stronger, or cheaper, all before we ever make a single physical object.
Okay, now for the bleeding edge. The last tool in the box isn't just a tool, it's more like an intelligent assistant. This is where we stop just telling computers what to do and start teaching them how to think like an engineer.
And this is a totally different way of thinking. Instead of programming a computer with the laws of physics, we just feed it a fire hose of real-world data. We hook up sensors that measure vibration, temperature, strain, you name it, and we let the machine find the hidden patterns of what works and what's about to fail.
So the process basically goes like this. First, you collect tons of data from a real working machine. Then you clean all that data up to get rid of the noise. Next, you feed that clean data into a neural network, which chews on it and learns the subtle little signs that show up right before something breaks. The end result?
a model that can look at a machine and predict its remaining useful life with scary good accuracy. And this is just a peek at the alphabet soup of crazy smart algorithms that make up this toolkit. Now don't worry about memorizing all these acronyms. Just know that each one is like a specialist. A CNN, for example, is amazing at finding patterns in images, so it's great at spotting tiny cracks. An LSTM is an expert at finding patterns over time, like listening to a machine's vibrations to predict when it'll wear out.
So let's zoom back out and put it all together. What happens when you have all three of these incredible toolkits, the foundational, the digital, and the intelligent, all working in concert? Well, it means we can understand and model our world better than at any point in human history.
You can really see that evolution right here. We started with the good, solid predictive power of those foundational formulas. Then we jumped to the high predictive power of digital simulations. And now, we're in a whole new era of adaptive prediction with these intelligent models that literally learn and get smarter over time.
And that's the ultimate payoff, right? It's about combining the strengths of all these tools. You use physical tests to make sure your simulations are accurate, and you use AI to monitor how things are performing in the real world. When you do that, you create systems that aren't just strong, they're smart, they're safe, and they are unbelievably efficient.
And that really leaves us with one last big question to think about. As these tools for seeing the invisible get even more powerful, what's next? What problems that seem impossible today will we be able to solve tomorrow? The possibilities are pretty much endless. Thanks for digging into this with me.